Good day! My name is Teacher Sally and welcome to our class. In Part 1, you have learned the plate tectonics and the evidence of continental drift. In this lesson, I will discuss the sea floor spreading and plate boundaries. Are you ready to learn? Then let's start. The question as to how the drifting took place left the continental drift theory blurry. Despite the evidences presented by Wegener, his idea that the continents were once joined together was not accepted by the scientific society until the 1960s. He was not able to explain how the drifting took place, and this made the scientists conduct further studies in search for the answer. Seafloor spreading is a process in which tectonic plates or large slabs of Earth's lithosphere split apart from each other. The main idea of this theory is that oceanic crust forms at ocean ridges and becomes part of the seafloor. During the 1950s and 1960s, new techniques and modern gadgets enabled scientists to make better observations and gather new information about the ocean floor. With the use of sonars and submersibles, scientists had a clearer view of the ocean floors. They have discovered underwater features deep within the ocean. Scientists found a system of ridges or mountains in the seafloor similar to those found in the continents. These are called mid-ocean ridges. One of these is the famous Mid-Atlantic Ridge, an undersea mountain chain in the Atlantic Ocean. It has a gigantic cleft about 32 to 48 km long and 1.6 km deep. The ridge is offset by fracture zone or rift valleys. Sea floor spreading and other tectonic processes are the result of mantle convection. Mantle convection is the slow motion of Earth's mantle. Convection currents carry heat from the lower mantle and core to the lithosphere. Convection currents also recycle lithospheric materials back to the mantle. Seafloor spreading occurs at divergent plate boundaries. As tectonic plates slowly move away from each other, heat from the mantle's convection currents makes the crust more plastic and less dense. The less dense materials rises, often forming a mountain or elevated area of the seafloor. Eventually, the crust cracks. Hot magma fueled by mantle convection bubbles up to fill these fractures and spills onto the crust. This bubble-up magma is cooled by frigid seawater to form igneous rock. And this rock becomes a new part of Earth's crust. Seafloor spreading occurs along mid-ocean ridge, large mountain range from the ocean floor. The Mid-Atlantic Ridge, for instance, separates the North American Plate from the Eurasian Plate and the South American Plate from the African Plate. The East Pacific Rise is a mid-ocean ridge that runs through the Eastern Pacific Ocean and separates the Pacific Plate from the North American Plate, the Cocos Plate, the Nazca Plate, and the Antarctic Plate. The Southeast Indian Ridge marks where the Southern Indo-Australian Plate forms a divergent boundary with the Antarctic Plate. Renewal of the ocean floor. According to this theory, hot, less dense material from below the Earth's crust rises towards the surface of the mid-ocean ridge. This material flows sideways, carrying the sea floor away from the ridge, and creates a crack in the crust. The magma flows out of the crack, cools down, and becomes the new sea floor. As the new sea floor is formed at the mid-ocean ridge, the old sea floor farthest from the ridge is destroyed at the subduction zone. Over time, the new oceanic crust pushed the old oceanic crust far from the ridge. The process of seafloor spreading allowed the creation of new bodies of water. For example, the Red Sea was created as the African plate and the Arabian plate moved away from each other. Seafloor spreading is also pulling the continents of Australia, South America, and Antarctica away from each other in the East Pacific Rise. The East Pacific Rise is one of the most active sites of seafloor spreading, with more than 14 centimeters every year. In the place where two oceanic plates collide, or where an oceanic plate and a continental plate collide, a subduction zone occurs. As the new sea floor is formed at the mid-ocean ridge, the old sea floor farthest from the ridge is destroyed at the subduction zone. The rate of formation of a new seafloor is not always as fast as the destruction of the old seafloor at the subduction zone. This explains why the Pacific Ocean is getting smaller and why the Atlantic Ocean is getting wider. If subduction zone is faster than the sea floor spreading, the ocean shrinks. When the sea floor spreading is greater than the subduction zone, then the ocean gets wider. The findings that support sea floor spreading theory are the following. First, rocks are younger at the mid-ocean ridge. Second, rocks far from the mid-ocean ridge are older. Third, sediments are thinner at the ridge. And fourth, rocks at the ocean floor are younger than those at the continents. The seafloor spreading theory contradicts a part of the continental drift theory. According to this theory, continents move through unmoving oceans and that larger, sturdier continents broke through the oceanic crust, whereas the seafloor spreading shows that the ocean is the actual site of tectonic activity. Third is magnetic reversals. What is magnetic reversal? How does magnetic reversal happen and how does it prove seafloor spreading? Magnetic reversal is also called magnetic flip of the Earth. As magma solidifies, the iron-rich minerals align with magnetic north like a compass. It happens when the North Pole is transformed into a South Pole and the South Pole becomes the North Pole. This is due to the change in the direction of flow in the outer core. Seafloor spreading was strengthened with the discovery that the magnetic rocks near the ridge follow a pattern, aside from the fact that rocks near the ridge are remarkably younger than those farther from the ridge. A magnetic compass tells us directions on Earth. It also proves that the Earth has a magnetic field. The needle of a magnetic compass usually points to the North Pole of the Earth, which is actually the South Magnetic Pole at present. The Earth's magnetic field is generated in the very hot molten outer core and has already existed since the birth of our planet. The Earth's magnetic field is a dipole, one that has a North Pole and a South Pole. Magnetic reversals happen many times in the past. The occurrence of magnetic reversals can be explained through the magnetic patterns in magnetic rocks, especially those found in the ocean floor. When lava solidifies, iron-bearing minerals crystallize. As these crystallize, the minerals behave like tiny compasses and align with the Earth's magnetic field. So when magnetic reversal occurs, there is also a change in the polarity of the rocks. Third is plate boundaries. The main idea of this is that volcanoes, mountains, and deep sea trenches form at the boundaries between the plates. In the illustration, it shows the different tectonic plates in the world, namely Antarctic plate, African plate, Arabian plate, Eurasian plate, Indo-Australian plate, Philippine plate, Pacific plate, North American plate, Caribbean plate, Cocos plate, South American plate, Nazca plate, and Antarctic plate. According to the plate tectonics model, the entire lithosphere of the Earth is broken into numerous segments called plates. What causes tectonic plates to move? This is one of the main questions that has remained unanswered since Alfred Wegener proposed the continental drift theory. The plate tectonic theory is the theory provided an explanation about the movement of the lithospheric plates. This theory evolved from the two former theories and was developed during the first decades of the 20th century. Plate tectonics is the theory that the lithosphere is made of rigid plates that float on the atmosphere. Tectonics is the study of the formation of the Earth's features. The Earth composition tells a story about itself, so it gives us clues to its past and proofs about the gradual and slow changes that it has undergone for over 4.6 billion years ago. In the illustration, it shows the different zone of the Earth that includes crust, outer core, inner core, and mantle. The crust is the thinnest and the outermost layer of the Earth that extends from the surface to about 32 kilometers below. Underneath some mountains, the crust thickness extends to 72 kilometers. The Earth's crust, as gleaned from the illustration, is divided into two regions, the continental crust and the oceanic crust. Now let's proceed to the different zones of the Earth. First is the crust. Crust is a thin, solid outermost layer surrounds Earth like a shell that surrounds an egg. So we have two types of crust. We have the oceanic crust and the continental crust. Oceanic crust means under the oceans. This is thinner, more dense, and basaltic rock, while the continental crust, it makes up the continents or the land, so it is much more thicker and it is less dense. It consists of granitic rock. The continental crust is mainly made up of silicon, oxygen, aluminum, calcium, sodium, and potassium. The thickness of the continental crust is mostly 35 to 40 kilometers. Continental crust found under land masses is made of less than rocks such as granite. The oceanic crust is around 7 to 10 kilometers thick, which its average thickness is 8 kilometers. It is found under the ocean floor and is made of dense rocks such as basalt. The oceanic crust is heavier than the continental crust. Second is moho. Moho is the boundary between the crust and the mantle. Third one is the mantle. Beneath the crust is the mantle, which extends to about 2,900 kilometers from the Earth's surface.
It makes up about 80% of the Earth's total volume and about 68% of its total mass. The mantle is mainly made up of silicate rocks, and contrary to common belief, is solid since both S waves and P waves pass through it. The attempt to study the Earth's mantle extended as far as studying the rocks from volcanoes, simply because they were formed in the mantle. Scientists also studied rocks from the ocean floor. They have determined that the mantle is mostly made of the elements silicon, oxygen, iron, and magnesium. The lower part of the mantle consists of more iron than the upper part. This explains that the lower mantle is denser than the upper portion. The temperature and the pressure increase with depth. The high temperature and pressure in the mantle allows the solid rock to flow slowly. Now is the lithosphere. So this is the rockosphere, or the upper part of the mantle, the cool and rigid. The crust and the uppermost part of the mantle form a relatively cool outermost rigid shell called the lithosphere and is about 50 to 100 kilometers thick. These lithospheric plates move relative to each other. Next is the asthenosphere, or the wick sphere. So it flows like hot tar and consists of plastic mantle or lower plastic mantle. Beneath the lithosphere lies the soft wick layer known as the asthenosphere, made of hot molten material. Its temperature is about 300 to 800 degrees Celsius. The upper 100 kilometers of the asthenosphere has a temperature enough to facilitate a small amount of melting and make it capable to flow. This property of the asthenosphere facilitates the movement of the lithospheric plates. The lithosphere, with the continents on top of it, is being carried by the flowing asthenosphere. Next is plasticity, or the ability of a solid to flow. Number 4 is core. The core is subdivided into two layers, the inner and the outer core. The outer core is 2,900 kilometers below the Earth's surface. It is 2,250 kilometers thick and is made up of iron and nickel. The temperature in the outer core reaches up to 2,000 degrees Celsius. At this very high temperature, iron and nickel melt. The inner core is made up of solid iron and nickel and has a radius of 1,300 kilometers. Its temperature reaches to about 5,000 degrees Celsius. The extreme temperature could have molten the iron and nickel, but it is believed to have solidified as a result of pressure freezing, which is common to liquids subjected under tremendous temperature. Now, what tells us that the inner core is made up of iron? Aside from the fact that the Earth has magnetic field and that it must be iron or other materials which are magnetic in nature, the inner core must have a density that is about 14 times that of the water. Average crustal rocks with densities 2.8 times that of water could not have the density calculated for the core. So iron, which is 3 times denser than crustal rocks, meets the required density. Some clues that the inner core and the outer core are made up of iron include the following. First, iron and nickel are both dense and magnetic. Second, the overall density of the Earth is much higher than the density of the rocks in the crust. This suggests that the inside must be up of something denser than rocks. Meteorite analysis have revealed that the most common type is chondrite. Chondrite contains iron, silicon, magnesium, and oxygen. Some contains nickel. The whole Earth and the meteorite roughly have the same density. Thus, the Earth's mantle rock and the meteorite minus its iron have the same density. Aside from the seismic data analysis, the Earth's magnetic field strengthened the idea that the Earth's outer core is molten liquid. The outer core is mainly made up of iron and nickel moving around the solid inner core, creating Earth's magnetism. Now, if we have never been there, how have we learned about the interior of the Earth? Determining the location of earthquake epicenter plays a vital role in laying the foundations of plate tectonics. By studying seismic waves. Seismic wave is a vibration that travels through the earth, results from earthquakes or huge explosions. You have learned in your grade 8 science that an earthquake releases 3 types of seismic waves: primary or the P waves, secondary or the S waves, and long surface waves or the L waves. The first 2 travel into the Earth's interior, while the last one on the surface. These waves travel at different velocities, thus do not arrive at a seismic recording station at the same time. The farther the recording instrument is from the focus, the greater the difference in arrival times of the first P wave compared to the first S wave. The difference in the arrival time will tell us the distance of the earthquake's focus from the seismic recording station. However, it does not tell us in which direction it came from. Now, let us discuss the different types of plate boundaries. The Earth's lithosphere is divided into several plates. As you have already learned, these plates ride over the weak atmosphere. There are 3 types of plate movements: separation of 2 plates or divergent, collision of 2 plates or convergent, and sliding past each other or transform. What facilitates the movement of the plates? Heat is produced in the core that produces convection in the mantle. Now, this convection causes the plate to move around. Studying plate boundaries is important because along these boundaries, the formation of the lithosphere is happening. These geologic events have a great impact not only on the environment but also on us. So let's have first the divergent boundary. Divergent boundary means 2 plates that are moving away from each other. As plates move apart, the atmosphere flows up to fill the empty space. Formation of plate valleys and oceanic ridge are indications that the crust is spreading or splitting apart. In this case, the plates are forming divergent plate boundaries wherein they tend to move apart. Most divergent boundaries are situated along underwater mountain ranges called oceanic ridges. As the plates separate, new materials from the mantle ooze out to fill the gap. These materials will slowly cool to produce new ocean floor. The spreading rate at these ridges may vary from 2 to 20 cm per year. Although a very slow process, divergence of plates ensures a continuous supply of new materials from the mantle. The Mid-Atlantic Ocean ridge is an example of spreading center which causes the divergence of the South American plate and the African plate. Now, what forms when plates diverge? First is mid-ocean ridges, or the Mid-Atlantic Ridge. Second is the rift valleys. These is narrow valleys in the middle of the ocean ridges and where continents separate, like the East African Rift Valley. When a spreading center develops within the continent, the crust may break into several segments. The breaking leads to the formation of down-faulted valley called Rift Valley. It is also associated with the rising of hot materials from the mantle. The Rift Valley increases its length and depth as the spreading continues. At this point, the valley develops into a linear sea similar to the Red Sea today. Second is convergent boundaries, means direct collision of one plate with another. We have three types of converging boundaries. First is the oceanic-continental convergence. Second is continental-continental convergence. And third is oceanic-oceanic convergence. Oceanic versus continental. Subduction zone is the oceanic crust that moves or dives under the continental crust. It forms an oceanic trench and volcanic mountain range. Oceanic crust is more dense than the continental, thus it dives down or subducts. From the diagram, it is clear that this event gives rise to the formation of a volcanic arc near the edge of the continental leading plate. The reason for this is because the denser oceanic crust, which is the plate A, undergoes what we call subduction process, or the bending of the crust towards the mantle. Since the mantle is hotter than the crust, the tendency is the subducted crust melt, forming magma. Addition of volatile material, such as water, will cause the magma to become less dense, hence allowing it to rise and reach the crust once again, and causing volcanic activities on the continental leading plate. For the oceanic crust, one important geologic feature is formed, and that is the trench, also called submarine valleys. Ocean trenches are the deepest part of the ocean. One of the deepest is the Philippine Trench with a depth of 10,540 meters. Another subsequent effect of the continuous grinding of plates against each other is the occurrence of earthquakes. The subduction of plate can cause earthquake at varying depths. Most part of the world experience occasional shallow earthquakes, where the focus is within 60 km of the Earth's surface. Of the total energy released by earthquakes, 85% comes from shallow earthquakes. Meanwhile, about 12% of energy originates from intermediate earthquakes of those earthquakes, with a focal depth range of 60 to 300 km. Lastly are the deep earthquakes whose origin is more than 300 km to 700 km the Earth's surface. The gravity at this subduction zone pulls the plate down. We have here some example of oceanic versus continental convergence. We have here Andes mountain range, Mount St. Helens and the Cascade Mountain Range. Second is oceanic convergence. Like the first type of convergent boundaries discussed earlier, converging oceanic plates will cause formation of trenches, and these trenches will become sources of earthquakes. Underwater earthquakes, especially the stronger ones, can generate tsunamis. The Japanese term for harbor wave tsunami is a series of ocean waves with a very long wavelengths, typically hundreds of kilometers, caused by a large-scale disturbances of the ocean. The leading edge of the subducted plate will eventually reach the mantle, causing it to melt and turn into magma. The molten material will rise to the surface, creating a volcanic island arc parallel to the trench. Volcanic island arc is a chain of volcanoes positioned in an arc shape. Many parts of the Philippines originated from the oceanic convergence. This resulted from the collision of two oceanic plates, with one of the plates diving under the other. This shows the formation of the Philippine archipelago. Aside from the formation of trenches and troughs, the downward movement of oceanic lithospheres underneath the Philippine archipelago creates active volcanic chains. Example, the descent of the West Philippine Sea oceanic lithosphere along the Manila Trench created a volcanic chain from Taiwan to Mindoro. Some of the known active volcanoes in this chain are Pinatubo in Central Luzon and Taal in Batangas. Also, the constant dipping movement of slabs induce frequent moderate to strong earthquakes at various depths, give rise to mountain range, and develops the geologic character of the Philippine archipelago. So we have here an example. We have Aleutian Island and the Mariana Trench. Last is the continental. So here there's no subduction. Two continental plates collide, pushing up and creating folded mountains. When two continental plates converge, a collision zone is formed. Unlike the other two types of convergent boundaries, subduction ceases for this particular type of convergence. No trench, no volcano, and definitely no island arc are created during this process. Instead, what is created is a large group of tall mountains called mountain range. About 40 to 50 million years ago, two large land masses, India and Eurasia, collided to begin the formation of the most visible product of plate tectonics, the Himalayas. Since subduction is impossible between two colliding continental plates, pressure is released by pushing the crust upward and forming the Himalayan peaks. Also, collision of continental plates is associated with shallow earthquake activities. So we have here an example of continental convergence, and that is Himalaya. The last type is transform boundaries. Here, the plates slide horizontally past each other. Remember that the presence of a ridge is an indication of diverging plates, and the plates diverge between the two segments of the mid-ocean ridge. The adjacent slabs of crust are grinding past each other. Although most transform faults are located within the ocean basins, there are few that cut through the continental crust. An example of this is the San Andreas Fault. Immediate concerns about the transform fault boundaries are activities triggered by movement along the fault system. This time, let's have the causes of plate motions. Convection current in the mantle cause plate motion. The convection currents rotate very slowly as they move and drag the plates along. Because of convection current, the tectonic plates are able to move slowly along tectonic boundaries, pushing each other, sliding past each other, and drifting away from each other. The hot, less dense rising material spreads out as it reaches the upper mantle, causing upward and sideward force. These forces lift and split the lithosphere at divergent plate boundaries. The hot magma flows out of the mantle and cools down to form the new ocean crust. The downward movement of the convection current occurs along a convergent boundary where the sinking force pulls the tectonic plate downward. As a substance like water is heated, the less dense particles rise while denser particles sink. Once the hot, less dense particles cool down, they sink, and the other less dense particles rise. This continuous process is called convection current. This is exactly what happens in the Earth's mantle. As an ocean crust moves away from a divergent boundary, it becomes denser than the newer ocean crust. As the older sea floor sinks, the weight of the uplifted ridge pushes the ocean crust toward the trench at the subduction zone. This process is called ridge push. Slab pull is the other possible process involved in the tectonic plate movement. The weight of the subducted plate pulls the trailing slab into the subduction zone, just like a tablecloth slipping off the table and pulling items within. Now, why do the plates move? So there's no single idea that explains everything, but we can identify several forces that contribute to the movement of the plates, and this includes the slab pull, which means the sinking of the cold, dense oceanic plates pulls on the rest of the plate. The ridge rises. The material deposited on the top of the ridge slides down from the rise, pushing on the plate. And of course, the convection, which is the movement within the mantle, could be part of the driving force behind the motion of the plates. Let us now have your activity. In the figure below, identify and list down the different tectonic plates in the world. You may type your answer in the comment box or you may write your answer in your notebook. Timer starts now. Alright, now here's the answer. Eurasian plate, North American plate, Juan de Fuca plate, Philippine plate, Australian plate, Pacific plate, Caucasus plate, Nazca plate, Caribbean plate, South American plate, Scotia plate, Antarctic plate, Arabian plate, African plate, and Indian plate. Congratulations! Now that you understand what happens inside the Earth and its effects on the Earth's surface, you should be able to realize that the tectonic activities at the surface, just like volcanic eruptions and the earthquakes, are inevitable. You should view the Earth as a dynamic planet and still the most fascinating planet, for it offers you a home that no other planet can. Thank you for listening and see you in the next lesson.